Alright guys, let's get started. Any questions you guys have on homework? You wanna start talking about? Yeah.
Are there keywords for the word problems or indicating specific data sets they want? Because sometimes I kept getting the wrong answer and I had to go back and figure out specifically what they were asking for in the different sets. I'm trying to like, what are the indicating words that say, I want this?
Okay, so this is a common question. Students often ask, are there keywords or there buzzwords that you can look out for to know what concept you can use? So unfortunately in this class, the short answer is no, and that's what makes this class so different and sometimes difficult for students, is that there's no neon sign that says, use this formula here, or use this concept here. So that's why this class is so conceptual, and you really have to understand the underlying concepts to know what what sequence of formulas you need to use. And that'll come with practice, and that'll come with asking questions and in case you need help.
Thank you.
Sure.
Yeah.
Any other questions you guys have? All right.
No, I'm done. He answered.
Oh, okay.
He asked, yeah.
Okay, good. Kill two boys with one stone, good. Any other questions?
I'm not dead yet.
Alright. So, so you guys do okay on the homework on counting?
I did, yeah, I did okay.
Okay. You guys do better with that, okay? No
Can
comment?
we get extra time on homework?
You have as much time as you need for the homework, and you can go back and do it again afterwards. It has to be completed by his deadline, but you can go back in and continue working those problems until you figure it out.
Well, I think that's what he meant, right? Extend the homework past midnight tonight.
Yeah, I should do that.
Maybe. You guys have questions on it, or
Some of us
need more help? Or? I'll consider it.
Or could we work on it?
So do you have key points that you want to go over?
The
The
homework's
last
not.
3 questions.
What is it?
The last 3 questions.
The last 3 questions.
Now you talking about yesterday's homework? Of yesterday's homework?
Yes.
Now the last 3 I remember. It was a pattern. The older lady taught me in the math lab, but she noted it. It was,
All right.
what it was, I gotta remember. 68, 99, 90 I believe. Is it 90? I got it right.
The percentiles?
Well,
Yeah, for the like percentiles?
Was it 97 point?
Yeah,
So-
you have to, it's
yeah.
like, you just use those numbers and use
Yeah.
in between.
Yes.
So it's like further. Yeah, I remember I do that.
Okay. So basically, you're given a percentile, you're asked to find the data point.
Yeah, like first, you have like number 1, 68, 2 is 95, and 3 is 99. And you have to like put it in that way.
Okay, so basically you have a data set, right? And then you're given a percentile, like, what, 67?
Yes.
And then we said that there's a formula that you can use to find the rank or the position
You have to
of the
draw.
number.
You have to like draw. Yeah. Let me see.
Draw a box plot.
Yeah, you have to draw it out, and you put like the mean, and then, you'll put like the distance between it.
I think you were given the mean standard deviation,
Yeah.
and then they asked, like, they would give you 2 numbers and ask what,
The
if that
distance-
was like 68%, 95%, or
What's the
90.
distance in between? What is it?
I don't know if that makes sense.
You're given the mean and the standard deviation.
Yep, and then it'll tell you like what percentile is 2 standard deviations away from the mean. And that would be.
Oh, okay. And are you told that that data set is distributed in a bell curve?
Yeah, that's what,
Oh, okay.
the bell curve.
Oh, okay, okay.
Yeah.
So that fits into one of the earlier topics that we talked about, where if you have a bell curve, there's this specific relationship between the percentage of the data in a particular range that's a fixed number of standard deviations from the mean. So we talked about,
Page 104.
yeah, page 104, thanks. So if you have a bell curve, the mean is always the number that's the most highest represented. So the mean is here. And then So we said that within one standard deviation,
68%.
yeah, 68%, good. So 68% constitutes the mean plus or minus one standard deviation.
Yes.
So then, that means that if you're given the mean and you're given the standard deviation, then you wanna find all values within 68%. Just, start with the mean and add and subtract one standard deviation on either side, and you'll come up with these boundary, points that represent the boundaries of this range of values that constitute 68%. Right, and then within two standard deviations, it'll be 95%, so you do the same thing if you're being asked for 95%. So that would be the mean plus or minus two standard deviations. And that's 95%. And then three standard deviations, happens to be 99.7. Should we do specific number? You guys okay? So remember we said that this relationship only applies to bell curves if you're given a percentage and the underlying distribution, you're told it's not a bell curve, or you're not told what the distribution is at all, you can't assume it's a bell curve, so you can't use this relationship. So in that case, you would use Chebyshev theorem to become that.
Okay.
Was there a question with that?
Yeah, it was a specific, example, but, I don't know if you wanna go over it.
Sure.
Alright, should I show you it?
What is it?
Should I show you it?
If it's long, otherwise you can read it. Yeah, so this is the same idea that we talked about. So within two standard deviations, that'll be the 95%.
Okay.
One standard deviation will be 68%. So here, you just find the number of standard deviations it actually is by subtracting one of these values, like 224, from the mean, and then divide by this to get the number of standard deviations.
Okay.
And then use that rule that we talked about.
Okay, thank you.
Cool. Okay, anything else, guys? Before we move on?
Do you believe you can pass the test?
Yes, I have full confidence.
When does it open?
Yeah, it opens Thursday afternoon, so after class tomorrow, and then it will be open until the beginning of next class, which is start Monday morning.
Well, maybe I should take it here with you.
Maybe you should do what?
I should take the test with you in here.
Oh yeah, yeah. That'd be great if that was that option.
You know, we can work together, we can work together.
Okay.
Send a video recording of you.
Let's review a little bit from last time. So we talked about counting. Let me do some examples that review those concepts. So let's say that you have holiday lights that you string in front of your yard. And so let's say that each light, let's say there are 20 lights. And each light has a toggle switch on it where you can control the color. Let's say red, green, or blue. Let's say that you've already strung the lights in your yard, and the only thing that you can adjust are the color of each light. So the question is, how many different color configurations are possible for the 20 lights? So a color configuration is, if you look left to right, how you strung the light, the order of each color would represent a different configuration. So how many different configurations? I don't know the exact number, but it seems like it should be higher than
20 by 20 by 20?
that. Okay, you're on the right track, but it's definitely more than
The same group.
any other guesses? Good thing we reviewed. Okay, so, last time we talked about a handful of concepts. We talked about counting, factorial, combination, permutation. But it's very tempting to just jump in and say, which of those is it? And which formula should I use? But what I recommend is, especially if you're just starting out, and I still do this, is start from basics and work your way up. Don't just jump into asking which formula it is. So, and especially in the beginning, if you're not sure where to start, then start listing out some example configurations that end up being counted within this total number. So if you have 20 lights here, one configuration might be light number 1 might be red, and then light number 2 might be green, light number 3 is green, light number 4 is blue, light number 5 is red, and so on. So this corresponds to the light number. And you keep going until you have 20 lights. And this is one configuration that ends up getting counted. This is important because just by this one example, you know what one possibility ends up looking like. So each possibility has how many things in it? It has 20 things in it. So then you can generalize this by drawing for each possibility or each configuration, you have 20 categories. So then for each of these slots, you ask yourself, how many options are there for each category here representing each position, each light position. So in this case, how many possibilities are there for the first light? Yeah, there's 3 represented by 3 colors. So same thing for the second light, you have 3 possibilities. Same thing for all the other numbers of lights. So by the rule of counting, you multiply all these together, and that would be 3 multiplied 20 times, which is 3 raised to the 25. So if you type this in, this is actually a huge number. This is over 1 million. Yeah, give me just an approximate.
3.4 billion.
3.4 billion. So this is a huge number that you're able to get very quickly without having to list out all the configurations to count them. But this is the exact number. Any questions? Okay, let's do the next related example. Let's say that instead of being pre-strung, these 20 lights being pre-strung on the electrical cord, let's say that they're loose in a box. So 20 lights in a box. Now let's say that you want to string all 20 lights into the electrical cord. And let's say the electrical cord has a fixed orientation already. One side is fixed, is already plugged in, and you can only string in one direction of the cord. I mention that because it just limits the possibilities, so you can't flip the electrical cord in order to get more possibilities. But one side is definitely fixed and plugged in, and so you can only string in from one direction. So you have 20 lights. The question is how many different orderings of these 20 lights are possible. So each ordering consists of all 20 lights, so how many different orderings? ideas?
That'd be the, exclamation point, right?
Okay, the suggestion is the factorial one. You guys agree? And why?
Cause it goes down all the way to one, so you go 20, then you have 19, then you have 18, then you have 17, but there's only so many ways that you can actually put that in, and the end result's gonna be how many different ways you can put that in.
Okay, excellent. So let me summarize that. So just like before, if you don't know where to start with some example configurations. So now an example configuration doesn't look like this anymore. It doesn't look like one of the three colors for each one. If you number the lights 1 through 20, now an example configuration might be in position 1, you might have light number 17, and then in position 2, you might have light number 6, and then light number 13, light number 9, number 5, and so forth, until you have a total of 20 lights. So this is one example configuration. So the question is, how many different possibilities are there, if you were to list them all out? And so just by looking at this, now you can generalize that each example configuration has 20 objects in it, so you can list that, your 20 slots. And then now you ask yourself, how many options there are for each category. So the first category here represents the first light position. And how many options do you have?
20.
Yeah, 20. You have 20 lights that you could put there, in which case you put one. And then after you put one light there, you have how many options for the second light? 19, good. And then so on, all the way down to 1. And then by the rule of counting, you multiply all these together. And by definition, this is factorial. So you're starting with a number, you're multiplying down one at a time until you get to 1. So this is 20 factorial. Any questions? So the answer here will be 20 factorial. All right, so let's do the next related example. So let's say that you have these 20 lights in a box, and again, we're assuming that they're all different. Let's say that the electrical cord only has room for 12 lights. So the question is, how many different ways can you string 20 lights with 12 at a time?
So NCR.
Okay, so we gotta be careful when we say NCR, that implies that order doesn't matter. That means if it's the same 12 lights, but in a different order, we still count it as the same configuration.
I thought it was P.
Okay, good. So if we want the order to matter, and we wanna count all the different orderings of the same 12 lights, then that would be permutation, or P. So let's build up to it. So basically, each configuration consists of 12 lights. And so for the first light, we have an option. We have 20 options, and then 19, and then 18, and so on. All the way down until we have 12 objects. So that looks like
8, right?
it should, well, it should be 90 because then you're including this actual number as well. So going from 9 to 20, there's 12 total numbers. Counting the 9 itself as well. Right, and then we said that if you were to just multiply all these possibilities together, then that means that you care about the order of the 12 that's in this group. And this is an important distinction because usually on a problem, you're never gonna be told, hey, order matters here, so that you know that you're supposed to use a permutation. So you have to basically decide whether that situation cares about order. So in this case, you have to ask yourself, if you have the same 12 lights on this string, on this electrical cord, then if you were to change the order of the same 12 lights, should that be counted as a second configuration, or is it still the same configuration? So imagine you have the same 12 lights, but in a different order. Should that be counted as a second possibility, or is that the same possibility? So imagine, instead of 12 lights, let's just do 3. So imagine, and then we can just generalize. So imagine you have 20 lights, but you string 3 at a time. So the first possibility is you have light number 11, and then light number 2, and then light number 17, strung in front of your house. But let's say that you take the same 3 lights and you string them in a different order. Should this count as 2 different possibilities, or should it count as the same one, because it's the same 3 lights?
2 different possibilities.
Yeah, it depends on the situation. In this situation, it would make a lot more sense that these are counted as 2 different possibilities because the ordering of the lights are dictating different possibilities. So these should count as different possibilities, so therefore we say that order matters within this group of 3, but in the original example, the group of 12. So if order matters, then we just multiply all the numbers and then we're done. If order doesn't matter, if the same 12 lights in a different order still represent the same possibility, because we only care about the identity of which 12 lights are on the string, then in that case we have to divide by the number of ways we can order the same 12 things. So divide by 12 factorial. But another way of saying that is instead of the original permutation, it's a combination. So if you just multiply, if order matters, then you would just multiply all these numbers together. And by definition, that's a permutation. So this is 20 permutes 12. This is order matters for the 12 objects. If order doesn't matter for the 12 objects, then that would be 20C12. So order matters, order doesn't matter. In this case, order matters. So it would be 20 per mu 12. So let's do the next example. Let's say that you have 20 lights in a box, similar situation. Again, all different. But let's say instead of stringing them onto an electrical cord, you want to select 12 lights so that you can put in a box and mail to your friend. So mail 12 lights. So how many different packages of 12 lights are possible? So starting, it's going to be the same situation because every box of 12 is going to have 12 lights in it. So then you list out your 12 slots, and then you ask yourself how many objects for each slot. So it's going to be starting out exactly this way. But then within each box of 12, you ask yourself, does the order of the 12 lights within each box matter? So for example, if you have the same 12 lights, but you change this order, should that count as a separate mailing? Or should that count as a different mailing? Or is it the same because it's the same 12 lights that you're mailing?
It's the same 12
It's the same 12 lights. So in that case, we say that order doesn't matter, and because of that, we use a combination here. So this would be 20C12. Okay, so that was a quick review in a nutshell of the major concepts we talked about last time. It includes counting, it includes factorial, permutation, combination. So let's continue what we talked about. So let's say that you had these three Scrabble tiles, and then these letters A, B, and C on it. And so let's say the question is, how many different ways can you rearrange all three Scrabble tiles? So how many different orderings are there of all three tiles? Like one ordering is this set ABC, another ordering might be ACB. So how many different orderings of all three tiles are there? Yeah, very good, 6. So we talked about this last time, this is just 3 factorial, because each ordering has 3 objects in it. There's 3 options for the first tile, or for the first position, there's 3 different tiles that could go there, and then 2 and then 1, so this is 3 factorial, or 6. But that's for the case where all 3 of these letters or objects are different from each other. So the question is, what happens if we have repeats? So what happens if the C happens to be a letter that already occurred, like A? So the question is, are there still 6 distinct ways to order these 3 tiles? And so this is a small enough number of possibilities, we can actually write them all out and count. So this is one. What's another possibility? Yeah, BAA, AAB, anything else? Okay, good. So you notice that if all 3 tiles are different, then there should have been 6. But if we don't have all different tiles, if one of them repeats, then you notice that we don't have 6 anymore. We only have 3 distinct possibilities. So now the question is, how do you come up with that number 3 quickly without having to do all this work and count everything by hand? Any suggestions?
Divide off the identical.
Okay, good. So let's build up to what it is. So in this case, just by looking head on, you can't tell the difference between the duplicate A's. But let's say that somehow you could distinguish them. Like you flipped the tile and you numbered the A's, for example. Let's say you can tell the difference. So if you could tell the difference between the A's, then how many possibilities would there be?
6.
Yeah, then we go back to the first case where they're all different letters and there's 6 different arrangements. So let's list out the 6. So this is one possibility. So I'll just list them all out. Okay, so these are the 6 if you can tell the A's apart. But if you can't tell the A's apart, then this first one is actually the same as which one? If the A's were indistinguishable from each other, and you couldn't tell the difference between A1 and A2.
Same as the second.
Yeah, it's the same as the second because the A's are the same. So if you can't tell the difference between the A's, then the first 2 collapse as being the same possibility. What about the third one? What's that the same as? Yeah, same as the fourth one. And same thing for the 5th one and the 6th one. These are the same. So you notice that there are these 3 distinct groups, and that's how we're getting the 3 distinct possibilities. So that's how we went from 6 originally, if all the 3 letters were different, down to 3 if we merge the ones that are the same because they have the same A's. in the same positions. So the question is, so basically, we have 3 total possibilities here. And the way that we can get 3 is if we start with the original 6 and divide by the number of ways that we can arrange the A's that are in the same positions. So how many ways can we arrange 2 things, 2 objects? So if you have 2 objects, let's call them X and Y, how many ways are there to rearrange those 2 letters? 2, X, Y, or Y, X, right? But in general, if we have 3 things, then it becomes 6, and so on. So it's basically just 2 factorial. And 2 factorial turns out to be 2 times 1, which is 2. So we have the original 6, which is 3 factorial, divided by 2 factorial, and that's how we're getting the 3 distinct objects, 3 distinct groups. Any questions so far? Alright, so let's ramp it up a little bit. So let's say that you had 3 repeating A's in a B. Based on what we talked about, how many distinct orderings do you think there are?
You said 3 repeating A's and a B?
Mm-hmm. Instead of the previous example, again, we had 2 repeating A's and a B. Now we have 3. Imagine these are Scrabble tiles, so how many different orderings of these Scrabble tiles are possible? If each ordering has all 4 tiles in it.
4 factorial divided by 3 factorial.
Okay, excellent. So just like before, we start by pretending they're all different, in which case there's 4 factorial orderings, and then we divide by the number of ways to order the duplicate A's that are in the same positions in each group. So here there are 3 duplicate A's that will end up being in the same positions, and we divide by 3 factorial. So 4 factorial divided by 3 factorial turns out to be 4. Any questions? Okay, so let's ramp it up a little bit more. Let's say we had 3 A's, 2 B's, and a C. So let's build up to this together. So we're gonna first start by pretending they're all different, in which case how many different tiles are there? 6. So if they're all different, there's 6 factorial ways to arrange 6 different letters. But they're not all different, so we want to divide out. So ultimately, we want to find how many total groups are there, and then we want to divide out by the number of orderings of each duplicate letter. So how many different orderings are there of the 3 A's within each group?
3.
That's 3 factorial, right? And then that's just the A's, but now we're going to incorporate a different letter. So how many ways to arrange those 2 duplicate B's?
So we have 2 factorial.
2 factorial. And then by the rule of counting, we're going to multiply down here. So this will be 2 factorial. And then for consistency, this C is showing up once, so you can do 1 factorial for the C, so that it doesn't feel left out. And also, if you do that, then you kind of have a way to check yourself, because all these factorials will add up to the total up here. So 3 plus 2 plus 1 down here add up to the 6.
That's awesome. Is that an always?
Well, yeah, if you include that straggling letter that doesn't repeat, then that's always true. But this is optional because 1 factorial is just 1, and divided by 1 doesn't change anything. So you can either include this or not. But if you include it, then you have a way to check yourself. Okay, So just as practice, go ahead and try entering this in your calculator, make sure you're getting the right result. Okay, good. Give me 60. Okay, so now you guys are pros at this, so let's have you try this one. Let's say the Scrabble tiles spelled out Mississippi. So how many different orderings are there? Okay, let's do it together. So you first pretend they're all different, in which case, how many different letters are there?
11.
Yeah, 11 factorial. And then divide out, let's look at each duplicate at a time. How many duplicate i's are there?
4.
There's 4, so then we do 4 factorial. And then the s's, also 4, so 4 factorial for the s's. The p is 2, so 2 factorial for the p. And then there's a lonely m here, we can do 1 factorial for that. But again, that's optional.
You get 3, 4, 6, 5, 0.
Okay, good. So 34,650 possibilities. It'd be a lot more if all these letters were different, but because you have so many duplicates, you end up having this number. Okay, any questions, guys? So in your book, that's called permutation with repetition. That's actually kind of a misnomer. So remember, a permutation is more general than a factorial. A factorial is you have to arrange all the total number, like all 6 in this case. Each possibility has to have all 6 things. But in a permutation, you're allowed to only take a subset of those and arrange them. So because in all these cases, each possibility has the total number of tiles, this should actually be called a factorial with repetition. But your book calls it a permutation with repetition. Okay, any questions? Alright, so another idea before we move on to the next chapter. Let's say I asked you to evaluate this expression, 100 factorial divided by all of 96 factorial times 4 factorial. So if you have your calculator, go ahead and try to enter this and let me know what you get.
Overflow error.
Okay, overflow error. Where's you guys getting that? Okay, so no matter what calculator you should be getting an error. Some calculators will just say error and leave it vague. Some calculators will specifically say the type of error, which is an overflow error. So anybody happen to know what that means? Yeah, so the issue is that whatever number, so as soon as you hit 100 factorial, you're gonna get this error right away. It won't even let you enter the remaining expression. So it turns out that 100 factorial is a number that is so big that it's too big for the calculator to hold, to handle. It can hold an approximate value, but it can't hold the exact value, because it would require too many digits. So it turns out that every calculator, every computer on Earth has a fixed amount of memory that it could dedicate to holding each particular number. And if a particular number is too big for that, the bit size, then you're gonna get an error. So that doesn't mean that this entire expression results in a number that is too big. It's just that in the intermediate steps, this particular number, 100 factorial, happens to be too big, and the calculator just conks out. So let's go ahead and try to evaluate this entire expression, but we're gonna have to toss the calculator aside for now and do this by hand. So it's not as painful as it sounds. We just have to understand what the definition of a factorial actually is. So 100 factorial, what does that mean?
Hundred of one and all combinations being multiplied together.
Yeah, so let's just do one expression at a time. So 100 factorial means start with 100 and multiply down one at a time until you get to 1. So we're just gonna list it enough. So that's the meaning of 100 factorial. And then let's do the same to the other ones. So 96 factorial, same idea. We're gonna start with 96 and multiply down one at a time until you get to 1. And then 4 factorial is just 4 times 3 times 2 times 1. So now you have an expression where you have all these numbers that are only being multiplied or divided. There's no other operation, there's no addition, there's no subtraction. So only multiplication and division. So in that case, you don't have to multiply all these numbers before you start dividing. So when you have a choice of only multiplication and division, you can divide first. So that comes from the fact that numbers can be multiplied in any order, and division is just a form of multiplication. So it also applies with division. So you can choose to divide first. So in this case, for example, you can divide this 96 by this other 96 on the bottom, and you just get 1. What other numbers can you do that with?
All the rest of them to one.
All the rest of them to 1. So now, in one fell swoop, you've gotten rid of 96 numbers on top and 96 numbers on the bottom. So if you just enter in the 4 numbers on top being multiplied, divided by the 4 numbers on the bottom, then that's definitely a number that the calculator can handle. And you'll get an answer. So this is one way that we could have done it. So the second way that you can do it is once you simplify it, you can see that the top of the fraction here is just 4 numbers being multiplied. So you can recognize that this is actually a mathematical operation, starting with a number, 100 in this case, and then multiplying down one at a time until you have 4 numbers total. By definition, that's what operation. If you go all the way down to 1, that's a factorial. But if you stop before you get to 1, and you only have 4 numbers being multiplied here, what's that called? So if you go all the way down to 1,
Order doesn't matter, so, because order doesn't matter, that's your combination.
well, in this case, we don't know if order matters or not. We don't have we don't have a conceptual situation. All we have is a mathematical expression. So we don't know whether or not order should matter here or not. So, but just by definition, we have a number being multiplied down one at a time. If we went all the way down to 1, that's a factorial. If we stop possibly somewhere before that, then that's a permutation. So the top part is a permutation, and it's 100 permutes, because you have 4 numbers, it's permute 4. So instead of typing in 100 times 99 times 98 times 97, you can just type in 100p4, that'll be the same result. But that's just the top part. And then the bottom part is 4 multiplied by 3 down 1, so by definition, what operation is that? 4 factorial, good. So, a second option you have is you can enter this expression in your calculator and get the same answer as before. So 100p4 divided by 4 factorial. Or you could recognize that this whole thing is actually one mathematical operation. It has a unique name, and what's that? Permutation divided by a factorial, where this argument of the factorial is the same as this argument. What's the name of that operation? That's a combination, very good. So this is actually the same as 100 combination 4. And you could have just typed in this one operation in your calculator and gotten the same result. So there's 3 ways that you could have punched this in. Okay, any questions? All right. So on every test, I ask some variation of this question, designed so that if you were to punch this in verbatim in your calculator, you'd get an error. On every test, invariably, I have at least one student who comes up during the test and asks, my calculator is broken, it says error. So now you guys know not to do that. All right, any questions before we move on?
So how many questions will be on the test like this?
One, at least one.
Just making sure, you know, maybe to learn a lot of points.
Yeah.
Can you make the test right?
The author of the textbook who makes the homework questions makes the actual test questions, but I curate them, I pick them out.
Okay.
So it's the same as the homework. The author of the textbook makes the homework questions that I pick out as well.
Okay.
Okay, so let's move on. This was section 4.4. We're gonna move on to the beginning of chapter 4 and talk about probability now. So in real life, when people talk about the probability of an event happening, what does that mean?
Possible but not guaranteed.
Okay, so if you're to ask to find the probability of this happening, what are you trying to find?
What are the likely chances?
Okay, good. So to find how likely that is of happening. So the probability of an event occurring is the chances that events will occur. So this is keyword that's subtle that I underline, and the reason I underline it is because we're trying to find the chances that a future event will occur. So the event actually hasn't occurred yet, but we want to find the probability that it will occur. So, given that we're trying to find the chances of a future event happening, how do you think people go about finding that probability if it hasn't even occurred yet?
Historical data.
Okay, very good. So this will be categorized under ways people find probabilities. So one way is to look at the past. Look at the past or look at the present, because both the past and the present are the past relative to the future. So look at past or present. So let's do an example. Let's say that you want to find the probability that somebody from Alaska will become president of the United States. And so one thing that you could do is you could look at past data. So you could look at all the presidents from the past, and how many have there been? About 46, right?
Yeah, 46.
So you look at all 46 presidents, and one at a time, you see whether they're from Alaska. And then you count the percentage of those that were from Alaska. And if you did it that way, then what percentage would you get?
0.
0, right? So if you tried to look at past data to estimate this probability of somebody from Alaska being president, then you'd get 0 out of 46, and you conclude that it's a probability of 0. Now, a probability of 0 means it's absolutely impossible. It could never happen in a trillion years. But is this necessarily true?
No.
Yeah, it's not necessarily true. So this is not the correct answer to the probability we're trying to find that a person will become president from Alaska. So what about this past data led us to an incorrect conclusion?
Because no one has been elected from Alaska.
Right, yeah, that's true.
You're making an incorrect assumption that since something hasn't happened, it never will.
Okay, very good. So you're making this incorrect assumption that just because it hasn't happened in the past, it never will. But then that begs the question of what does the past data have to look like for us to trust the results of that past data for the future?
There's only 46 data points.
Okay, excellent. So this past data actually only has 46 data points. So if you're gonna rely on past data, you need a lot more data points than that. So one important assumption of looking at past data is that the size of the past data needs to approach infinity. So the larger the data size, the better in being able to trust your past data to reflect the future. What else about this past data is leading us to an incorrect conclusion?
There might have been 46 presidents, but there are 50 states that a president could come from.
Okay, good. So one way that we can summarize that is that this past data needs to be reflective of the future that we're trying to predict, or representative of the future that we're trying to predict. Because for a long time in history, Alaska wasn't even a state. It wasn't even a possibility for somebody to become president from Alaska, but it's not even a state. So today and in the future, Alaska is a state, so we need data that is more representative of that fact. So the past data needs to be representative of the future we're trying to predict. So these two assumptions in trying to predict the future by looking at the past, we need our past data to have a size that approaches infinity, i.e. large enough, and also that past data needs to be representative of the future we're trying to predict. So these two requirements, that should feel kind of familiar. So what does that sound similar to?
Population sample?
Okay, very good. So remember on the first day of class, we talked about this issue of trying to make a conclusion about the whole population using a sample. So in this case, we're trying to make a conclusion about the future using past, but same idea, is that our data needs to be large enough, just like before, and it needs to be representative. Okay, and so because this data of looking at the 46 past presidents doesn't fit both these assumptions, that's why it's giving us inaccurate results. And this is not good past data to look at in order to make this prediction about the future. Any questions? So that was a counterexample of not being able to use past data. So let's use an example where we might be able to use past data to make an accurate future prediction. So let's say that you're interested in knowing whether this particular coin, let's say that you want to find the probability of heads for a certain coin. And so let's say that you look at past data or present data to try to find this, and you find present data by just flipping it on the fly. So let's say that you flip this coin a number of times that approaches infinity, like let's say 1 trillion times. And so after you flip the coin 1 trillion times, then you count the percentage of heads for this coin, and then you report that result as being the future probability that you'll get heads for this coin flip. So is this an accurate way to find this future probability of heads for this coin? So basically, we're trying to find this future probability of heads for this coin, and we're trying to do that by looking at past or present data. And in this case, the data is present because we're generating observations on the fly. And so in order for us to get an accurate conclusion about this future probability, these assumptions about the past or present data needs to be true. So let's see if both assumptions are true. So is the size large enough? Is it approaching infinity? Yeah, because we're flipping it a large number of times that approaches infinity. What about the second assumption, that the data needs to be representative of the future? So what that means is if you're trying to find the probability of heads for this particular coin, then when you flip it in the future, then if you flip it now, it needs to be the same flipping conditions for the same coin. So if you flip the same coin under the same atmospheric environmental conditions, then yeah, it'll be representative of the same coin that you're trying to make a prediction about later. But on the flip side, if you take this coin and you go to the moon and you flip it and you count the percentage of heads there, that's not going to be representative of the same coin flipped here later on, right? So that's why this will be an accurate way to find the probability of heads, because both those assumptions are wrong. But what's the issue of doing this? The issue is that you have to flip the coin 1 trillion times. That's a lot of coin flips. And we don't have the time or patience to do that, and sometimes we don't even care that much. So we want a faster way to find this probability. So one way is looking at past or present data, but the assumptions are pretty stringent. And sometimes we don't have the luxury of those assumptions. So let's look at another way to find this probability. So the other way is mathematical. We'll talk about several mathematical ways to find probabilities, but let's start with one. So one way is called the classical definition of probability. So the classical definition of probability says that the probability of a desired event is equal to the number of desired events divided by the total number of events. Or number of events. So, for example, if we were to use the example of this coin, if you look at a coin, how many events total are there for that one coin?
Two.
Yeah, there's 2 events possible for that coin, heads or tails. And of those 2, how many are desired, which in this case, if you want the probability of heads, the desired event is heads. So of that coin, there's 1 desired event, which is heads, and so probability would be 1 out of 2. But this has a big, big assumption associated with it. This 1 out of 2 is only true for what? What case?
For something with only 2 possibilities.
Well, if the coin is fair, then the probability of heads is 1 out of 2. If the coin's not fair, where one side is weighted differently, then all bets are off. The probability of heads is not necessarily exactly 50%. So, one way that we can summarize the assumption that needs to be true is that these 2 events that are possible need to be equally likely of occurring. So it must be equally likely to be heads as tails for each foot. So the important assumption is that all total events must be equally likely. So for example, if you have a coin that is not fair and it's weighted differently on one side than the other, and you try to find the probability of heads by looking at past data and flipping it 1 trillion times, then you might get something like 70, or like, let's say 79% heads, if you actually flip it 1 trillion times. In that case, the probability of heads for that unfair coin would be 79%, or 0.79. But if you try to use math, and you say, oh, the total events is 2, and heads is 1 of them, and so probability of heads for this coin must be 1/2. Well, that's not true, because that assumes that the coin is fair, and that all events are equally likely. Heads and tails are equally likely. So this math only works if all events are equally likely. Any questions? Okay. So this issue of equally likely is really important. Let me do an example. Let's say that you have marbles in a jar, and each marble has a particular color and has a particular pattern. So let's say the colors are either red or blue, and the patterns are either solid or striped. And you reach in and select 1 marble. Let's say you're blindfolded. And you select 1 marble randomly. So the question is, what's the probability that that you select a marble that is both red and solid? So one way that you can find this probability is by looking at past and present data, by repeatedly drawing marbles out, 1 at a time, but a number of times that approaches infinity, like 1 trillion times. You draw 1 marble out, each time putting it back in, and at the end, you just count the ones that ended up being red and solid. So that's one way that you could find this probability, by looking at past or present day. Another way is, let's try this classical definition of probability. So the probability of this desired event of being a marble that's both red and solid will be the number of desired events divided by the number of total events. So in this case, what would be the number of total events?
18.
Okay, so if you counted all the individual marbles, you'll get 18. And of those, how many are being desired? In that they're both red and solid, there's 3 of them. So this probability will be 3 out of 18 simplified to 1/6. So that means the probability is exactly 1/6. That means that if you were to actually conduct this experiment in real life and draw 1 trillion marbles, then exactly 1 out of 6 of them will end up being red and solid. I say exactly 1/6 with a disclaimer, is that the closer you are to infinity, an infinite number of experiments, then the closer this will get to 1/6. Okay, so here, the number of total events we chose was 18. But let's say that I had played devil's advocate and I said, well, you desire these 3 marbles that belong in this group, and there's 4 groups total. So why shouldn't the answer be 1 group out of 4 for the answer instead of 1 out of 6? So why shouldn't the answer be 1/4?
Because all of them are in the same pot, they're not individual groups, they're all together, and you're reaching into the same pot to pull them out, so you'd never get that 1/4. The other part is, the numbers aren't all the same, so you're not, it's not the sample, but your, other variable, doesn't match the one that you're trying to find.
Okay, excellent. So another way that we can phrase that is that to use this classical definition of probability, there's an important assumption that needs to be met, which is all total events have to be equally likely. So if you choose these 4 events as being your total events, then you're saying of these 4, each of the 4 is equally likely of occurring. So are these group of 6 marbles equally likely of being drawn out or pulled out of the jar as these 3 marbles in this group? No. These 6 marbles in this group are twice as likely as being drawn as the marbles in this group. So these 4 are not equally likely. So that's why you can't put the 4 down here, representing your total events. But the correct answer, when we put the 18, are these 18 individual marbles equally likely of occurring?
Yes.
Yeah, so each one has an equal opportunity of being drawn, so that's why it was correct to put 18 on the bottom of this fraction and not the 4. Okay, and that's what we mean by this assumption of all events need to be equally likely. Okay, so we're still on the mathematical approach to finding probability. So let's go back to the example of trying to find the probability of somebody from Alaska becoming president. So let's say you try another approach and you say, oh, there are 50 states, and Alaska is one of them, so the probability should be 1 out of 50 that somebody from Alaska will become president. You guys agree with that? No, why?
I'm going to a different direction entirely, because the requirements to become president are clearly listed in the Constitution. It says what you have to have and be to be eligible to become the president, period.
Okay.
Right, so it's not on who, what, when, where, or why, but it's like, if you meet these qualifications and apply for it, you can become president. What they've done on the research polls behind that one is saying, to run for the primaries and get your name put into the election, getting your name known generates the highest likelihood of being selected to be a candidate from it, and none of it is talked about where anybody comes from.
Okay, so why isn't there a 1 out of 50 chance?
Wouldn't that mean that there's 1 person per state?
No, this means out of every 50 people, well, 1 person will end up being president. So in other words, yeah, out of every 50 candidates, 1 will be from Alaska.
Okay, so let's say that first it goes by the population in Alaska. Second, like how you're raised. I mean, some people, if you live in Alaska, I don't think that you think about president, you think about like really surviving, hunting, you know, how cold it is.
Okay, okay,
So, you know, they already feel like, you know, they're by themselves, so.
very good. So all you guys are saying the correct thing, and basically to summarize that, this will only work if these 50 states have equal representation, meaning they're equally likely of having somebody from Alaska from each of the 50 states. So we're saying that somebody from Texas should be equally likely to be president as somebody from Alaska. And from experience, is that true? No, it seems much more likely that somebody from Texas will become president. And the reason for that is there's a lot of factors associated with it, like the population of Texas is a lot bigger than the population of Alaska. The political dynamics is a lot different in Texas and Alaska, and so on and so forth. So all these different factors are making this assumption that these 50 states are not equally likely of producing somebody to become president. And so this assumption is not true, and that's why you can't do this. Any questions? Okay, so there's an important assumption that needs to be true if you're going to use a mathematical approach to find probabilities, is that all events have to be equally likely, and this is hard to have in real life. So of these two ways, they both have stringent assumptions. Let's look at a third way that people can find probabilities.
I'm not trying to interrupt you, I just wanna make sure I understand that particular part for the mathematics one isn't that almost like a bias? That it has to be equally true, because if it's not, and you have a biased result, it's not gonna give you a, useful result.
Yeah, so basically, if you tried to say Alaska is one of the 50 states, so the probability of becoming president from Alaska is 1 out of the 50, well, you're assuming that all the 50 are all equally likely in the same way, and Alaska is one part of that equally likely pot. And so, unless you know what all the individual weights are, then you're not going to get the correct answer. So that brings us to the next way that people find probabilities in real life. Which is what we call a subjective approach. So the word subjective in real life is in contrast to objective. So in real life, when we say that something is subjective, what do we mean by that?
Dependent upon?
Yeah, well, kind of. So objective means that there's objective truth, means that it's factual, versus subjective means that it's subject to opinion. It's opinion based. So basically, this subjective approach is just a fancy way of saying that we don't know and we're going to use our best guess. So this is really the best guess approach. So back to the example of finding the probability that somebody from Alaska will become president. We acknowledge that there are all these different factors that have all different weights. For example, to be from Alaska, every state has a different population size that contributes to it. Every state has a different media influence, and that might have something to do with it. Every state has a different political history that has something to do with it, and so on. So you have all these different factors that are all weighted differently. So that's all those different variables are very hard to quantify. So sometimes the best we can do is just weigh all those variables in a hand-wavy kind of way, and just saying, well, I'm gonna try to internalize all these weights the best I can and use my best guess. And so sometimes, oftentimes, that's what people do to try to estimate probabilities, is they'll just use their best guess. And so I mention that because if you see a certain probability thrown out at you, sometimes it'll look like a very exact number. But if it was calculated one of these two ways, looking at past data and a mathematical approach, and the assumption were true for each of the methods, then those methods will be accurate. But if that probability was given to you as a best guess, then sometimes it might not be accurate at all. So you'll have to consider that when you're given a certain probability. Any questions? So in this class, we're going to focus on this mathematical approach. First of all, because this is a math class. And second, if the assumptions are actually met for the mathematical approaches, then you're going to get the most accurate answer possible. And sometimes in real life, the assumptions can't be met, but sometimes in real life, the practicality is close enough to the assumptions that we can get an answer that's very close to ideal. So in this class, the examples we're going to use are examples that will fit the assumptions perfectly, like rolling dice or flipping coins. In those cases, we're going to get assumptions that are perfectly matched. Any questions so far? Okay, so in the time we have left, let's talk about some mathematical approaches to finding probabilities. So, like before, let's talk about that marble example. We have marbles in a jar. We have each one being a color and a pattern. So either red or blue is the color, and either solid or striped for the color, or for the pattern. So the first question is, what's the probability that a marble is just red?
1/6, 1/18.
Yeah, so before we did the probability of red and solid, but now it's just red. So we have to count everything that fits this description of being red. So these three that are both red and solid happen to be red, but what else is red? Yeah, the five striped ones are also red. So basically, everything in the first column is red. So if you add everything in the first column, you'll get 8 out of 18. And you can simplify this, but we'll just leave it so that you know where the numbers came from. Okay, so next question we'll do together is, let's say you want to find the probability that a marble is either red or solid. So just like before, we're going to basically use this classical definition of probability, count the number desired divided by the total. So we just want to count the total number of marbles that fit this description.
So you got 8 or 7.
Yeah, so just count all the ones that are either red or solid. So these three happen to be either red or solid. They happen to be both red and solid, but that counts as being red or solid. And you have these 4 that happen to be solid, so that's either red or solid. And you have these 5 that are red and striped. And what about these 6? they're not counted because they're neither red nor solid. Right? So you have all these that fit this description. If you counted them up, how many are there?
12, 16.
Yeah, 12 out of 18. So it turns out that this probability that we just found has a very specific structure. And the structure is you have a probability of two events that are joined by this word or. So this is in contrast to if the two events were joined by the word and. What would the probability of the and be? And means that in the same event or the same marble being drawn, both of these events have to be true in the same event.
So that becomes back to the 3.
That comes back to the 3. So the point is, there's a big distinction between the words and that connect the two events versus the word or that connects the two events. So or means it could be either one being satisfied, and it means that both need to be satisfied in the same event.
So the answer is 3 over 18.
Yeah, so in this case, the and, that would be 3 out of 18. So it turns out that the first one we did, the one with the or, has a very specific structure. It's a probability of two events joined by or. So in that case, there's a mathematical principle that applies to that, and we call that the addition rule. So the addition rule says that in general, if you have two events joined by or, probability of A or B, that you can separate out into two separate probabilities that are joined with addition. So this is the same as the probability of just A plus the probability of just B. But then there's an extra term, so minus the probability of both A and B together. So again, the addition rule applies to a probability of two events joined by or. If you have that probability of A or B, then that's equal to the probability of just A plus the probability of just B, but minus the probability of A and B together. So let's apply this rule to our situation here that we already know the answer for, 12 out of 18. We're going to use the addition rule on this. So the addition rule applies to probability of two events joined by or. In our case, we have the probability of red or solid. So event A will correspond to red, event B will correspond to solid. And then we're just gonna match the template of the formula. So this is the probability of A plus probability of B minus both. So let's just fill it out in words first, before we fill in the numbers. So the probability of A in the formula is the probability of what event? Of red. Plus the probability of B, which is solid. And then minus the probability of
Red and solid.
red and solid. Okay, so now let's fill in the numbers. What's the probability of just red?
Just red was 8.
Yeah, 8 out of 18. Probability of solid,
Is 7.
7 out of 18. And then minus the probability of both red and solid.
3, 18.
Yeah, that was the 3 out of 18. And if we simplify this using the addition rule, then that was 15 minus 3 all over 18, which is 12 out of 18. which is exactly the same answer that we got before, without using the addition rule. So the point here is that the addition rule works. It matches the answer that we got without the addition rule. Let's talk about why it works, maybe some intuition for why it works. So before we used the addition rule, all we did was just count up everything that matched this description, being both red and solid. And basically, it was the sum of these circled events, 3 plus 4 plus 5, that gave us the 12 out of 18. But if we look at the addition rule, let's see what it's doing. It's adding the probability of just red. So just red will give us basically the first column, and then if we take the probability of solid, that gives us the first row. And if we add these two together, what do we end up adding twice?
The 3.
Yeah, the 3. There's an overlap here where it gets added up twice, and we just want to add everything up once. So that's where this extra term in the addition rule comes in. We have to subtract out the overlap. And that's why this is really the same thing as making sure you add up everything once. Any questions? All right, so that's the addition rule. Let's talk about the next related idea. So let's talk about conditional probability. So let's say that you reach in and grab a marble, but let's say you happen to be blindfolded, you don't see what color it is. And I tell you, oh, that marble's red. So now that you know that the marble is red, what's the probability that the marble is solid? So another way that we can indicate that is the probability that the marble is red, given that the probability the marble is solid, given that it's red. So this is called a conditional probability because we're trying to find a probability knowing that a certain condition has occurred. And this is abbreviated with this notation, the probability of solid, and then vertical bar, and then red. So the thing that comes after the vertical bar is the condition that we assume to be true. So this is read as the probability of solid given red. So again, that's if you reach in and I tell you it's a red marble, then now what is the probability that the marble's solid? So to find this actual number, another way to say this is out of only all the red marbles, what fraction of those are solid? So instead of all previous 18 marbles, now it's only out of all the red marbles. So how many red marbles are there? 8. There's 8. So out of these 8 red marbles only, what fraction of those 8 are solid?
3/8.
3. So the answer here would be 3 out of 8. So what if I had these same two events, but they were in a different order? So let's say I had probability of red given solid. Do you think that should be the same probability? Yeah, it turns out that in general, these are very different ideas. So maybe sometimes coincidentally, they end up in the same number, but conceptually, they're different ideas. So this is saying, out of all the solid marbles, what fraction are red?
3/7.
Yeah, so out of the 7 solid marbles, 3 of them are red, so this would be 3 out of 7. And you see it's a different number. Questions? Okay. Okay, so the next related question is before we already found this probability that a marble is both red and solid. He said that was what?
3/18.
3/18. But it turns out that just like with the case of probabilities with or, this is a probability with and this has a mathematical rule associated with it as well. And the mathematical rule is called the multiplication rule. So the multiplication rule has to do with probability of events joined by and. So if you have the probability of A and B, this is equal to the probability of A times the probability of B, given that A occurred. So let's go ahead and apply this multiplication rule to the example that we already know the answer to. So we want to find the probability of red and solid. We'll call the event before the and event A, and the event after the and event B. And now we'll just fill it in the formula. So probability of A will be the first event, which is probability of red. And then times
Probability of being solid.
solid given that it's red. Okay, so let's fill in the numbers. So probability of red in this case is, okay. So red, not just red and solid.
8/18.
Yeah, 8 out of 18. Times the probability of solid given that it's red. So out of all the red, what fraction are solid?
3.
Yeah, out of all these red, there's 8 of them. And then 3 of them are solid. So then if you look at this, this is all multiplication and division between these numbers, so you can choose to divide first. So you're gonna get 3 out of 18, same as before. So this is the multiplication rule that applies to the probability of events joined by and. So to summarize the important things we've done so far, we have this multiplication rule, which is the probability of events joined by and we have the addition rule, which is the probability of events joined by or. And we saw that using those two mathematical rules, we get exactly the same answer as if we just looked at this and counted using classical definition of probability. So you might be thinking, well, that's all well and good that you're getting the same answers for these mathematical rules, but it's a lot easier just to look at it and count. So what's up with these rules?
What we're using and looking at is relatively small. When you're dealing with something that's much larger, it would be much easier to use a mathematical rule than try to sit there and individually count every one of those.
Yeah, very good, very good. So here we have a very small data set, and also we know the individual values of every single point in the data set. Versus in real life, you're not gonna know that. You're gonna have a very large data set, and you might have some summary statistics on the data set, but you won't know every single point. And so the summary statistics you'll have is you'll know the probabilities of things, individual things, but you won't know the individual values. And so because of that, you'll see that these rules end up being very fruitful, very advantageous later on. Right now, we're just seeing that you're getting accurate answers by using these mathematical rules. Okay, so the next idea we have before time's up is this last idea we'll talk about today, which is the idea of complements. So you notice that the way I spelled complements here, this is spelled with an E instead of complement with an I. So compliment with an I means that you're complimenting or praising, flattering someone. But compliment with an E means something different. Do you happen to know what this means?
Because, complement of event A, denoted by A consists of all outcomes in which the event A does not occur.
Okay, okay. What does that mean in English?
The total.
Okay, so let's back up a little bit before getting technical. So in real life, when people talk about compliments, but with an E, what do they mean? This is actually a term in life as well. If two things complement each other, for example,
They go
two
with each
people
other?
complement each other. Okay, very good, very good. So when you say that two people complement each other, for example, you're not only saying that they work well together, they go well together, you're also actually saying that they complete each other. Which means that if somebody is weak in something, then the second person actually makes up for it, fills in the gaps, and vice versa. So another way of saying that is that actually the two people with their deficits add up to form a complete person. And so that's also what we mean in the mathematical sense.
That a politician has never been given a compliment.
Yeah, sorry. Well, that's complement with the I, but this is complement with an E.
Oh no, I definitely meant it with me.
Oh, okay, okay. So the complement of a situation is basically what it takes to complete that original situation. So, for example, if I look at an event that corresponds to, let's start easy. Let's say that I say a certain event is red marble. So let's call this event A. So the complement of A is everything that is left over that could occur that fills in the gaps of what this is missing. So if a marble's not red, then what else could it be to complete this entire set of possibilities?
Blue.
Yeah, blue. So if you add up all the red marbles and the blue marbles, then you get the entire event space. So the complement of being a red marble is being a blue marble. Let's practice a little bit. And the complement of A is actually represented by the mathematical symbol of the original event A, but there's a horizontal bar over it. So the complement of A is A horizontal bar. So let's say that you have an event A which represents that a marble is both red and solid. This is a little bit tricky, so what would the complement of A be?
Blue and striped.
Yeah, so we want something that describes all the situations that are left over. So basically, a way to describe all the marbles that are left over. So I think one suggestion I heard was blue and striped, but if you look at blue and striped, that's actually only these six. We want some description that captures all the remaining marbles, the 4 plus 6 plus 5. So we're on the right track, but it's not quite blue and striped because that would only be these six.
Blue or striped?
Okay, very good. So if you say blue or striped, we're able to capture everything that's left. So the complement of red and solid turns out to be either blue or striped. So it turns out that the idea of the complement is useful because if you take the probability of an event and add the probability of its complement,
what do you think you should get?
The total of your sample?
You should get the total, which is 100%, and 100% is 1. So the probability of A plus the probability of A complement has to be 1. And so if you look at these examples, if we did the probability of an event A is that the marble's red, then what's the probability that a marble's red? 8 out of 18. And we're saying that this rule has to be true, so that if you add the probability that a marble is not red, or blue in this case, what's the probability the marble's blue?
10.
Yeah, 10 out of 18. So by this complement rule, this indeed, if you add them up, this has to equal 1. Because you get 18 out of 18, which is 1. And same thing for this case, if you take the probability that a marble is both red and solid, and you add in the probability of its complement, then you're going to get 18 out of 18, which is 1. So the probability of an event plus the probability of its complement has to add up to 1. And so this is useful because sometimes it might be hard to calculate directly the probability of an event. But sometimes it's easy to know the probability of its complement. So if you know the probability of its complement, how do you calculate the original probability you want? Yeah, you subtract it from 1, very good. So the probability of the event you want, if you know its complement, is simply 1 minus the probability of the complement. Okay, any questions? All right, so we've covered the main concepts in chapter 4, but we haven't done practice together. So what I'll do is the homework on this section, I won't make it due next time, I'll make it due Thursday night instead. So so start doing as much as you can on it, and then we'll have tomorrow to discuss as well. And then I'll make the homework that was originally due today, I'll make it due tomorrow.
Love you.
Love you too, guys.